So this second MFPS session is a special one. So we're going to have 4 30-minute talks by people connected to the late lamented Phil Scott, who died last December. So this is a session in memory of Phil Scott, and I'm very pleased to be able to be sharing it. And I'll endeavour to make sure. Apparently, we have to leave the building in a timely fashion at 5:30. So, without further ado, I'm going to hand over to Rick Blute. Rick is the organizer of this session, and he's also going to be the first speaker. So, over to you, Rick.
Thank you, Andy. And I want to show my deep appreciation to the organizers of this conference, or these 2 conferences, for proposing this special session in honor of Phil. And I know I speak on behalf of Phil's wife, Marcia, as well, that she really very much appreciated it. So thank you to everyone for that. So I moved to Canada in 1991 for 2 years, and I never left. And that was largely because of Phil. So I was offered a postdoc at McGill. And after that, those 2 years were up, Phil managed to convince the University of Ottawa to offer me a second postdoc. And then after that, a tenure track position. This, in spite of the fact that apparently the phrase, "not another damned category theorist," was being tossed around the math department freely. But Phil did convince them. Apparently that math department meeting was quite interesting. And here I am. And so Phil had a huge impact on my life. He was the best man at my wedding. But he also had an impact on my life at an intellectual level. And that was largely because of this wonderful book. I knew even before I got to graduate school that I wanted to do category theory for a living. But it was this book that convinced me to go into categorical logic and categorical proof theory, because it's such an elegant way of thinking about these topics. And I immediately wanted to start doing this stuff. And I know that for practically everyone in category theory at around my age, when we were reading this book, we were having the same sort of reaction. And so even though the ideas of this book have now percolated pretty well into the category theory community, I do want to take a minute to just say the basic ideas of the book. And the basic idea is this. It's called categorical proof theory, and you can take a logical system and build a category out of it. What you do is your objects of your category will be formulas, and the arrows will be equivalence classes of proofs. And what that equivalence class is usually the tricky thing to figure out, but we have some general guidelines on how to do that. And when you do that properly, the results are remarkable. So in particular, if you take just plain old intuitionistic logic and just even take the conjunction implication fragment of it, then when you do this construction to it, you get a Cartesian closed category. And that already to me is surprising and interesting and good evidence that this is a good way to think about things. But in fact, you can say more than that, because that category is the free Cartesian closed category generated by the atomic formulas. And furthermore, there's a canonical way of representing the morphisms in that category. Remember, a morphism is an equivalence class of proofs, but that equivalence class can be represented by a simply typed lambda term. And so that the resulting category is the free Cartesian closed category. And so, to me, that ends the question. This is a really good way to think about logical systems. And so if I do have such a category, then I have this adjunction, and the co-unit of this adjunction becomes the usual modus ponens rule for logic. Stuff that you can explain to people who don't know anything about category theory will at least recognize that without any problem. And similar remarks hold for linear logic. So I was very lucky in that I was a graduate student at the University of Pennsylvania, and both Phil and Jean-Yves Girard, the inventor of linear logic, were spending time there. And so I got to be in the ground floor while all this stuff was happening. In fact, those of you who know linear logic, the 102-page paper that introduces the subject, Girard was writing it while I was there. So that's the sort of basic theory. But now the next idea was to extend this to what are called polymorphic types. And this begins with the observation that a lot of programs work the same when they're instantiated at different types. The behavior of the program is the same regardless of what type you're thinking of. And a trivial example is the identity type. That's the program that does nothing, but it does nothing in the same way whatever type you is instantiated at. And so that's called the polymorphic identity. And so the idea behind functorial polymorphism, and this is due to Stuart Bainbridge, Peter Fried, Andrei Shedrov, and Phil, is that in this situation, we want to represent types as functors, and then programs would be natural transformations. There is a lambda calculus corresponding to this called System F. It was independently defined by John Reynolds and Jean-Yves Girard. And so basically we were looking for ways of modeling that. And so this seems like a good idea, but it's not. And the problem is the most interesting polymorphic types aren't functors for a stupid reason. So the type alpha implies alpha is not a functor in general. There are ways you can fix this, simply because the variable alpha occurs simultaneously in a covariant and a contravariant position. And so there are sneaky things you can do, like talk about categories where you have a morphism in each direction. These are categories of embedding projection pairs, and you use that fact to get around this problem. But in some sense, that's not the most natural way of doing it. Is there something else we can do? And the answer is yes. And this is where functorial polymorphism really starts to work. So the solution is, instead of looking directly at alpha arrow alpha, I'm going to look at it as a specific instantiation of the functor, which, and this is a genuine functor. Alpha implies beta, which goes from C op cross C. I forgot the op there. C op cross C to C. And instead of looking at natural transformations, we're going to look at dinatural transformations. The di here stands for diagonal. So Phil loved to talk about functorial polymorphism, dinatural transformations. Every couple of years, one or the other of us would give talks on this to our students. And when I was cleaning out his office, I found his slides. And so I thought I would use his slides to present this stuff. So a dinatural transformation. So suppose I have two functors from C op cross C to D. Now, those are two functors with the same domain and codomain. So I can talk about ordinary natural transformations between them if I wanted. What would that be? It would be a family of arrows indexed by pairs of objects from C, such that the usual square commutes. But instead of that, I'm going to just look at the diagonal. So I'm going to instantiate just on single objects A, and I'm going to look at a family of morphisms of the form FAA to GAA. And when I do that, I can't talk about the squares anymore. I can't write down that the square in a way that parses. Instead, I have hexagons forced on me. And so a hexagon that looks like this. And here's the equation that hexagon has to satisfy. Notice that on the top path, it goes first contravariant, then covariant. And on the bottom path, it goes first covariant and then contravariant. And I have to have this hexagon commuting. So this was invented, this notion was defined by Eduardo Dubuque. It's a more general, there's a more general thing defined by Max Kelly called extranatural transformations. This is a specific example of that. This is the right level of generality for what we wanted to do. Oops, wrong button. And there's lots of examples of dinatural transformations. This isn't just some idea that popped up out of nowhere. A lot of the interesting multivariant constructions in mathematics are dinatural. So a boring case, if you take F for G just to be ordinary, either covariant or contravariant, so you project out half of the domain, then you just get ordinary natural transformations. But now I can talk about, for example, a natural transformation from a covariant functor to a contravariant functor. And if you gave this to a student who knew any category theory, they'd come up with this definition. But now we see it as an instance of the more general notion of dinatural. I can talk about, here's an interesting example. So I have the constant functor, so I'm in say the category of sets. I have the constant functor evaluated at the terminal object, and I have the multivariant functor blank to the blank. And then a natural transformation, a dinatural transformation, becomes something that satisfies this equation. And an interesting question is it the case that there is one in any closed category? There's the transpose of the identity, that always works. But an interesting question is, if you're in a category, some kind of closed category, is that the only one? And the answer is sometimes yes, sometimes no. In the reasonably concrete categories like sets and vector spaces, you can prove that that is the only one. This is an instance of something called full completeness, which I'll come back to in a minute. Here's another example, evaluation at a fixed object. So I fix an object D, and I look at functors of the form d to the blank cross blank, and then to the constant functor evaluated at D. And so evaluation is an example of a dinatural transformation. And here's the equation that you would like it to satisfy. And then I can let D vary. And then I have general evaluation, which goes from blank to the blank cross blank to just blank, and I get that equation. So this, oh, and here's one more example, church numerals. So church numerals go from blank to the blank to blank to the blank. And if you give me an endomorphism of A, I map it to that endomorphism composed with itself n times. That's a dinatural transformation. So as I said before, all sorts of interesting constructions are dinatural, and they are typically things that can't be expressed using ordinary natural transformations. And there's the equation that would satisfy. So this seems like a great idea. What I'm going to do is I'm going to look at multivariant functors, and I'm going to look at dinatural transformations between them. And this seems like a great idea. And in fact, this seems, oh, wrong button. I blew my joke. This seems to be going places. So Phil was a great guy who had extremely questionable taste in music. In particular, he was a huge fan of Herb Alpert and the Tijuana Brass. And I was desperately trying to figure out a way to work in a Herb Alpert album cover into this talk. And there it is. By the way, this is by no means the most ridiculous Herb Alpert album cover. And if you have a warped sense of humor, I invite you to investigate this on your own. But seriously, this seems like a great idea, right? I will look at dinatural transformations between multivariant functors, and that should be a model of polymorphic type theory. Yes. Keep hitting the wrong button. And furthermore, the equations that you want your polymorphic types to satisfy actually are equations that you want to hold, right? So if you go to a type theorist who doesn't care at all about category theory and show them the equations on those last few slides, they'll say, yes, those are precisely the equations that I want my polymorphic types to hold. And in particular, and if you're in a more complicated case where it's not obvious, then the dinatural transformation could actually suggest, here's an interesting equation that my polymorphic program might want to satisfy. So that's the idea. Let's take a Cartesian closed category. I will look at, my objects will be multivariant functors on that Cartesian closed category. My arrows will be dinatural transformations. And that is obviously a Cartesian closed category, right? But no, this doesn't work either. And this is the most annoying thing you could possibly imagine, because this category, in quotes, has products. It has the product objects, it has diagonals, it has projections, all that stuff's there. And it has the internal Hom, and it has the unit and the co-unit of the adjunction. All of these things are there, so the whole thing works fine. But dinatural transformations need not compose. So let me jump ahead for a minute. So I know that the two inner hexagons commute, and I put them together to make a big hexagon. I cannot conclude that the outer hexagon commutes based on the commutativity of the two inner hexagons. So this is just ridiculous. And so this is what we used to call a Cartesian closed non-category. And so what you need to do if you want to do this sort of semantics is build a category of dinatural transformations which do compose, and that is a non-trivial business. And in that first paper called Functorial Polymorphism, Baber, Schride, Shedroff, and Scott give an example of dinatural transformations which actually do compose the way you would want them to. And it's a construction on categories of partial equivalence relations. It's not really relevant to what I'm going to say today. But the point is, it's a very non-trivial construction, and it only works once. It's this category. It's not a general construction that will get you lots of examples. So what else can I do? Do I have time to do the example? Oh, yeah. Okay, so here's an example. It's on the category of finite dimensional vector spaces, or any compact closed category for that matter. I'm going to define a dinatural transformation from I to V star tensor V, which is pick an orthonormal basis and sum over EI star tensor EI. This is the transpose of the identity, right? Where you're using the isomorphism between A arrow B and A star tensor B. That's that. Okay, that's a dinatural transformation. And the second one is just evaluation. So that goes in the other direction. So that goes from V star tensor V to I, and that takes a element of the dual space F and an element of V and evaluates F at V. That's also a dinatural transformation. The composite of these two things should be a dinatural transformation from the constant functor at I to the constant functor at I. And if you unravel what that amounts to, a dinatural transformation between constant functors should just be a single map. But this composite is not a single map. It's basically multiplied by the dimension of V. Okay, so this isn't, so the composite of these two dinaturals doesn't commute. By the way, those of you who know linear logic and know about proof nets and the short trip condition, the long trip condition, I mean, will guess correctly that the reason these don't commute is it's a failure of the long trip condition. The way to think about this is in terms of what a linear logician would call axiom links and what a category theorist might call Kelly-MacLane graphs. Is this. And so I get a cycle. And whenever you have those cycles, the dinaturals won't commute. There's lots of other examples. You can look in, Phil and I have a couple of papers on this. In the very first paper, the functorial polymorphism paper has examples. And they all have this sort of flavor that there's a cycle being formed. And that's what screws up compositionality. So the follow-up was a general construction that will give us lots of categories of dinatural transformations which compose. And so the theorem is for any sensible logic, and so in particular, intuitionistic logic including or multiplicative linear logic, either intuitionistic or classical, all of those sorts of things, this works. And what it says is that if you have a categorical semantics for your logic, the interpretations of cut-free proofs will always be dinatural. And the proof is a straightforward induction on the complexity of the cut-free proof. And that's why you have to say cut-free here, right? So let's take a look at an example. So here's a step in the induction process. So suppose I have two proofs, one of K entails F and one of G entails H. And I've already proved by induction that those have dinatural transformations associated to them. And I want to attach a dinat to the proof where I combine these using the left implication rule, which is written there. And then the way that works is you then, is this the, you get, you have two hexagons by assumption. You have this hexagon and this hexagon. Those both exist by assumption. And then you show that you can combine those two hexagons into a bigger hexagon using just standard equations in Cartesian closed categories. And so you do that for every sequent calculus rule except cut, and it works. I think, if I remember correctly, this is the most complicated one of the bunch. Some of them are quite easy, like, for example, contraction and weakening. You're just composing with those with ordinary natural transformations, and then that makes it, that's easy to see that that's a dinatural. Okay, so cut-free proofs give me dinatural transformations, and now I can use the machinery of proof theory because in ordinary proof theory, the cut rule is used to string proofs together. in categorical proof theory, as in the book Lambeck and Scott, the cut rule is used to compose morphisms. And so I would use the cut rule to compose the morphisms attached to these cut-free proofs, and then I would apply Genson's theorem. So Genson says, in the original setting, before the existence of category theory, that every proof that can be derived with the use of cut rule can also be derived without the use of the cut rule. And the proof is algorithmic in nature. And so therefore, so before I get to the therefore, that familiar Genson rule is reinterpreted in categorical proof theory as saying that every proof that uses the cut rule is equivalent to, under that equivalence relation I talked about at the beginning of the talk, to a cut-free proof. Okay, and in fact, this is a good way to actually figure out what the equivalence relation is. As I said, the algorithm of cut elimination is an algorithm. It's a step-by-step thing. You convert all the steps in that process into your equivalence, and it generates an equivalence, and that ensures that this proof will work. And so I can now say that the dynats that we constructed using the sequent calculus from cut-free proofs, those dynats will compose. I simply find the proof with cuts that corresponds to the composition, eliminate the cuts, and that will be a dinatural transformation corresponding to my proof. So this is a nice example of a class of dynats that composes. And so this is the point that I came into the conversation, and we were aware of some nice work being done in game theory on something called full completeness. So full completeness is completeness with respect to proofs rather than just provability. And there are two papers on the subject. One is by Samson, Abramsky, and Rada Jagadisan, and they obtained full completeness for MLL plus mix, and Martin Hyland and Luke Ong got it for plain old MLL. And I want to show you the structure of the proof. And it doesn't matter if you don't know anything about game theory and you don't know what any of these terms mean. The point is, those two papers constructed categories where your objects are games and your arrows are strategies. And both papers gave an intrinsic game theoretic condition which picked out those games, those strategies, which correspond to proofs. So that's what history-free and uniform history-free and winning means. And those were the proofs. Okay. Again, it doesn't matter if you know about those definitions. That it's the structure of the proof that's important. And so, as I said, this is completeness with respect to proofs as opposed to provability. And so Phil and I realized that if we could do this in a category, in a star autonomous category, then if we get a full completeness theorem for cut-free proofs, we can then use the previous idea to compose those proofs. Because in a in a situation where you have full completeness, the correspondence between syntax and semantics is so tight that that syntactic proof will work. And so I'm going to skip all the details and just tell you that there is a category of topological vector spaces introduced by Solomon Lefschetz. He called them linear topological vector spaces, which is not a great term. So we renamed them Lefschetz spaces. And the key point is this category is a star autonomous category of topological vector spaces. So in other words, it is a model of multiplicative linear logic plus mix in this case, because the unit is the base field. And in fact, this category is the category that led Mike to write down the definition of star autonomous category. It's one of several. So what we did is we said, we're going to consider formulas interpreted as multivariant functors on this star autonomous category of vector spaces. And then we will look at dinatural transformations between those functors. And we'll call that the proof space associated to the sequent F entails F prime. I'm missing an F prime there. And our theorem is that and it's a vector space, that's trivial. It has as its basis the interpretations of cut-free proofs. And because we have this sharp correspondence between syntax and semantics, I can conclude, therefore, that those dinatural transformations compose. And it also works in the nice thing about linear logic. One of the nice things about linear logic is you can do non-commutative linear logic. And there's a version of non-commutative linear logic called cyclic linear logic. And we proved the same theorem for cyclic non-commutative linear logic, where we look at dinatural transformations invariant under the action of a non-co-commutative Hopf algebra. And thank you for listening.
Are there known classes of dinatural transformation that compose?
Where they don't come from this sort of theorem.
Sure.
Not off the top of my head. I'm sure there are.